So, hi everybody, I'm Idan. I want to thank the organizers and especially Daniel for inviting me. So the talk today, it's going to be a little bit mathier than usual, I guess. And it's math being done on a PowerPoint slide, so that's a complicated endeavor. Bear with me. So I'm going to talk about the discrete logarithm problem, which is kind of the mathematical object underlying most, if not many, if not most, cryptographic systems today. So I'm going to kind of give like a group recap, quick one, present the problem, and talk about ways to try to solve the problem. Okay, so cryptography generally and discrete log is done on many kinds of groups, but we in this talk not going to care about different kind of groups. So let's just have in mind the group ZP star. ZP star is the group that the element is 1 until p minus 1, and the action is multiplication modulo p. Okay. Examples, so Z star 11, the elements are 1 to 10, and let's multiply some stuff. 3 times 5 is 15. When we mod out 11, we get a 4. 6 times 7, 42. We mod out 11, we get a 9. 10 times 10, that's 100, which is also 99 plus 1. So when we mod out 11, we get a 1. Great. And next thing I want to define, to have in mind, the notion of exponentiation. As you all know from like general calculus, exponentiation is just taking a group element and raising it to the power of some integer, which means multiplying it by himself x times. Examples, the 11 star, elements are 1 to 10, 2 to the 6 is 64, we mod out 11 to get a 9. 7 times 3, you're going to trust me that it's 343, which is, again, you're going to trust me 31 times 11 plus 2. And so when we mod out 11, we get a 2. And if we multiply the two of those, well, we get 2 times 9, which is 18. When we mod out 11, to get a 7. So that's the only kind of group you should have in mind throughout this talk. Maybe not 11, maybe some very large prime, but so that's it. So why do we care about exponentiation? Exponentiation turns out to be a one-way function. And what do I mean by a one-way function? It means that exponentiation is easy. In terms of computing, it's an easy task. If you get a group element g and you get an integer x, raising g to the power of x is an easy task. Very, very efficient. However, the inverse operation is very difficult. You get two group elements, and you want to find an integer x such that g to the power of x is equal to h. And that is already that is a hard task. And as usual in cryptography, when people say hard, that only means that smart people were thinking about it for a long time, and they don't know the answer. So that's hard. And so the discrete logarithm problem, or DLP, is just this. Given g and h, two group elements, we want to compute an integer x such that g to the power of x is equal to h. Are we good so far? So kind of to give you motivation for breaking discrete log. The following are discrete log based: Diffie-Hellman key agreements, L-gamma encryption, Schnorr signature scheme, your favorite ZK snark, BLS signature scheme, Peterson commitment scheme, Shamir secret sharing, and many, many more. And underlying moral is that, well, if you break DLP, you break all of these, and breaking all of these is the end of the world, or the beginning of you having a lot of money. So Our goal today is to describe 4 algorithms for solving discrete log problem. And, well, the first method is the naive method of just performing an exhaustive search or brute force. So, brute force, we get an input, 2 group elements, G and H, and we want to output an integer such that G to the power of X is equal to H. And the algorithm is as follows. You compute G, G squared, G cubed, and so on, and you hopefully hit H after some time. So what's the running time of this? Is on the order of the group size, right? If the number of elements is n, then on average, after O of n steps, you will find a solution. So that's bad. You can imagine groups having a size whose like described with 1,000 digits, and so that's difficult. And the question is, can we do better? And the answer is yes, we can do better than O of n, but not much better than O of n. We can do O of square root n, and we can do slightly better than that, but not more than that, and I guess that's a good thing. And so I'm going to describe the next 3 more sophisticated algorithms, I guess. The first one is called baby step, giant step. So again, input, 2 group elements, G and H. We want to output an integer x such that G to the power of x is equal to H. And the observation underlying this specific method is the following. If the group size is n, then there exists 2 integers, a and b, such that x can be written as a plus b times the square root of n. And a and b are small, are something between 0 and the square root of n. So this may seem cryptic, but it's exactly like saying that 57 can be written by 7, a digit, plus 5, which is another single digit, times the square root of 100, right? A and b are small, and we just multiply by square root of 100. And this a, it's like fine-tuning, that's the baby step. And the larger steps are the giant steps, what we multiply by the square root of n. So now you kind of have to do some math in your head, but an equivalent statement to x being equal to a plus b times square root of n is that h is equal to, when we plug in x and we get h is equal to g to the power of a plus b square root n, or this statement, h times g to the power of minus b square root n is equal to g to the a. And I want you to kind of stare at this equation and notice the following. The right-hand side depends on a, and the left-hand side only depends on b. And we only have to check it for square root different options of a and b. We have square root options for a, square root options for b. And if we find an equality, then we found x. And so we create 2 tables, one for the left-hand side of the equation, and another one for the right-hand side of the equation. And we take the AB from equal entries, and those AB will form X. So let's try to make this clearer with an example. So we consider like a small prime, 113, and g is equal to, say, 3, and h is 57, and let's find the discrete log. So group size is 112, which is, the square root of which is roughly 11. So we only count up to 11, and we construct the 2 tables, one for different values of a, and one for different values of b. And we look for equal entries. In this case, the equal entries are where a is equal to 1 and b is equal to 9. Right? You can see the entries, the corresponding entries are equal. This implies that h times g to the power of minus 1 minus 9 times 11 is equal to g1, and we move stuff around to get that x is equal to 100. In other words, 3 to the power of 100 is equal to 57 mod 113. Yeah, so, yeah, question?
Is there any variant that uses less than square root n in memory?
So that was going to be my point exactly. So what just happened here? What just happened here is that we improved the running time complexity from n to square n, but we paid square n storage complexity. So we have a runtime memory trade-off. The runtime complexity is O of square root n, just creating the tables. And the space complexity is also O of square root n, which is storing the tables. And actually storing the tables can be much more of a hindrance than actually the running time. You know, time is infinite, just run the algorithm for a long time. So it is generic though, I mean, it applies to any group. Okay, so I have this remark there that I forgot to mention, that actually this running complexity of O of square root n is kind of provably the best you can do. I mean, perhaps you can do much better for specific groups, but for like a black box group, a group which you don't know any details, implementation details about, this is actually the best you can do. So the next algorithm I want to present is called Pollard's law. Oh, yeah, sorry?
Yeah. So it seems to a bit contradict the thought that this problem is hard only because we believe that smart people tried to solve it and didn't succeed against the provably lower bound for with square root of n. So can you maybe?
Yeah. So yeah, let me try to mitigate that. So for a black box group, yeah, it's provably the best you can do over square root n. However, for specific crypto systems, use specific groups, ZP star or field extensions or elliptic curves, specific groups. And for specific groups, you can do, you can do much better. And that's where the smart people didn't make it thing enters. So we had brute force and we had baby step, giant step. And the next thing we're going to do is have the same running complexity, runtime, the same runtime, but with no storage. Or, well, negligible storage. So here we go again. Input G and H group elements, and we want to output the discrete log. And the observation this time, the underlying observation is that if we know, I don't know why would we know that, but if it happens that we know A, B, A prime and B prime, such that this equation holds. GA, HB, GA prime, HB prime. If we happen to know that, that's great because we can move stuff around and get the G to the power of A minus A prime divided by B prime minus B is equal to H. And so we have X. So, okay, where can we get this equality from? I guess the naive way would be to kind of generate a random sequence. G to the power of A0, H to the power of B0. And then we generate another random element, G to the power of A1, H to the power of B1, and so forth and so on. And when we get a collision, we're good. We broke discrete log. But how long should it take to find such a collision? Let me recall the birthday paradox. if you generate random elements from a set, you are likely to get a collision in time which is roughly the square root, right? So that's where kind of the square root comes from. But so far, we didn't solve the space issue, the storage issue, because we have to store this entire sequence if we want to be looking for collisions, right? So we're going to do something a little bit more sophisticated. So suppose F is a mapping from the group to the group, which is a pseudo-random map. It's a deterministic function that kind of appears random, like a hash function. Hash function is just that. And we define the following sequence. We choose some random element, x0 from the group, and the next element is defined by applying the function f. So x1 is equal to f of x0, x2 is equal to f of x1, x3 is equal to f of x2, etc., etc. And the sequence that we get, well, it's random if you think of x0 as random, but it's a deterministic sequence that appears random. And so the birthday paradox again implies that we get a collision in O of square root n. Same problem though, we have to store the entire sequence. And the solution to that is the following that seems cryptic at first. So instead of storing the entire sequence, at any point of time, we only remember xi and x2i. If those are equal, great, we solve discrete log. If those are not equal, then we throw them away and we look we observe the next pair. So I'm going to try and convince you that this actually works. So we have xi and x2i. If they're equal, then we're done. If they're not equal, we compute the next pair, xi plus 1 and x2i plus 2. And yeah, I want you to look at this illustration. It starts at x0, and we apply f to go to x1, we apply f to go to x2, we apply f to go to x3, etc., etc., etc. And after applying it many, many times, we get a collision. The collision is right here. x10, we apply f, we go back to x4. So in other words, x11 is equal to x4, x12 is equal to x5, x13 is equal to x6, etc. Right? And the collision here just happens because, well, the sequence appears random. So let me try to convince you that if we look at xi and x2i, then we will get a collision. I mean, collision in the sense that xi, after enough time, after enough iterations, xi will be equal to x2i. So I have like a red dot and a blue dot here. And at first, they are both at x0. After one iteration, they are at x1 and x2, which are different. x2 and x4, which are different, so I throw them away. And the next pair is x3 and x6. They are different, I throw them away. x4 and x8, different, I throw away. x5 and x10, different, I throw them away. And you kind of see where it goes, right? Now, the next 2 points are x5 and x6, which is actually not x5 and x6, but x12 and x6, right? And after I iterate again, well, I get that x7 and x14 are equal. Yeah, so bottom line, we only have to remember xi and x2i, and after enough time, they will meet each other. So, okay, that's great. So let's make a few observations. The total path, this total path, is of size O of square root n. Why? Because that's how long it takes to find a collision in the sequence, right? But now, okay, you can tell me, fine, this path is of size O of square root n, but maybe those 2 points make many iterations inside the cycle before they meet each other. Why not, really? I mean, they can iterate forever in this cycle. Why would they ever meet, if at all? And so I'm going to claim that kind of the rabbit catches with the turtle before the turtle computes the round. And why is that? Let's take I want to take the animation a little bit back. And I want to observe a specific point in time. And the specific point in time is this one. The point in time where the blue dot enters the cycle. So when it enters the cycle, the distance between the blue dot and the red dot, well, in this illustration, it's 1, 2, 3 steps. But it can't be more than the size of the cycle itself, right? Because both of them are inside the cycle. So that's one thing to notice. The next thing to notice is that after every iteration, we close the gap. We close the gap by 1, because the blue dot makes 1 step and the red dot makes 2 steps. So put these 2 facts together. First fact is that the distance is not more than the cycle itself, and the second fact is that we close the gap 1 step at a time, and you get the fact that the red dot is going to catch the blue dot before the blue dot actually completes the first cycle.
So actually, like in worst case scenario, it will take as much as the size of the cycle in the case that they both start already in the cycle.
Exactly. If the blue dot is here and the red dot is here, then it's going to take exactly 1 round. That's the worst case scenario. And yeah, that's it. So we're going to find a pair, xi and x2i, before we complete the cycle. So before O of square root n. And what you need to notice here is just the fact that we only remember 2 group elements. So average runtime, O of square root n. Again, this algorithm applies for generic groups. It is randomized, unlike what we've seen before, and the storage is negligible.
Wasn't your goal to find the X4?
The goal to find X4?
The 2 points that lead to X4?
To X4? Why X4?
The direct collision.
No. I wanted to find a pair, xi and x2i, such that these 2 group elements are equal. Perhaps I said something misleading. When I said collision, I meant maybe a collision in the sequence or a collision between the pair. Yeah. And so, well, we're done with baby step, giant step. We're done with Pollard's law, which takes the same time but with negligible storage. And the next one is, it's actually more, I guess, cutting edge. It's not for generic groups, it's for specific groups, but for those specific groups, it's better than the other methods. So I decided not to kind of describe this algorithm in its most generality because it's kind of complicated, but I just decided to kind of follow an example. And I think that you can kind of get the idea from the example. So, index calculus. Yeah, there is something I wanted to say here. Oh yeah, I wanted to say that, yeah, I forgot about that. Baby step, giant step, well, you kind of understand where the names come from. We make giant steps, we make baby steps. Pollard's rho, it's because we have this like kind of image of a tail with a cycle. Index calculus means nothing. Don't linger about it. Index is just like a number theoretic term for a discrete log. Yeah. So let's proceed with an example. So we consider Z star 229, and G is equal to 6. And before we compute the discrete log of something, we're going to we do kind of a pre-processing, and we want to calculate the discrete logs of a few primes, 2, 3, and 5. And well, we're going to do that by guessing. What do I mean by guessing? So you see there is this 100 there. I just guessed it. I took a number, random number. I computed what is 6 to the power of 100. It happens to be equal to 180, which is not special other than the fact that I know how to decompose it to these specific primes 2, 3, and 5. Okay? And now, by applying logarithm on both sides of the equation, I get that 100 is equal to, well, 2 times log 2, 2 times log 3, and another 1 time of log 5. That's a linear equation. That's nice. I'm going to guess again. This time, the random number that I generated is 1, and 6 to the power of 1 is 6, which equal to 2 times 3. And again, I'm taking discrete log, and I get another equation. I repeat. So 6 to the power of 63 is 8, which is also decomposable by 2, 3, and 5. And this is not a general fact. Actually, roughly 20% of the numbers between 1 and 228, only 20% of them are decomposable by 2, 3, and 5. But I was guessing and guessing until I found some numbers that are decomposable by 2, 3, and 5. And so I got 3 linear equations, independent ones. That's an important thing to notice. And I solved this linear equation to get the solutions. So now I have the discrete log of 2, 3, and 5. Great. So what is going to happen now is that we're done with the pre-processing, and I'm going to use this pre-processing to compute the discrete log of something new. So let's compute the discrete log of 77. And perhaps you're wondering why not do the same? Why not, well, do the same, I mean, as we did in the previous slide. And the reason that we can do that is that 77 is not decomposable to 2, 3, and 5, or at least we don't know how. Okay? So, but there is a key, there's a little trick here that says that it is enough to have 77 times g to the k for some k and have that be decomposable by 2, 3, and 5. And if we take x equal to 0, then we get again a 77, which is not decomposable. If we take 13, then we get a 202, which is not decomposable. And we have to keep guessing. And if we take 156, well, it turns out that it's equal to 150, which is decomposable. That's great. And we take the discrete log of this equation to get that the discrete log of 77 plus 156 is equal to this linear combination of the discrete logs that we have already calculated. And we solve it to get 196 And bottom line, it turns out that 6 to the power of 41 is equal to 77 modulo 219. And that's the index calculus. That's it. You compute the discrete logarithms for some primes, and then next time you want to compute something, you can use the pre-processing.
The main idea is to use small primes, right? That are, the decomposition of many elements in the group.
Yeah, so the main idea is to have like a set which you can decompose many group elements to powers of elements in this set.
Does it help? What's the trade-off when you want to use more primes or less primes? Like,
Yeah, well, if you take more primes, then the pre-processing is longer,
yeah.
but then the second step is faster. By the way, now that you have completed the second step, you can add 77 to the set of like primes. I mean, the fact that I took primes is unimportant other than the fact that many numbers decompose into primes. Yeah, so that's it with the index calculus. So what did we have here? Well, the fact that the choice of primes dramatically affects the running time. Perhaps by looking at this algorithm, you don't know what is the running time because it's complicated. It depends on how many primes you're looking for. How long does it take to find independent linear equations for these discrete logarithms? And then you have to find, again, something that decomposes into these primes to get a new discrete log. So you kind of really have to fine-tune the choice of primes here. And then you will get this very nice sub-exponential running time. I mean, you shouldn't really, you can ignore it. It's a threatening number, but it's sub-exponential.
This is for any group?
No. You heavily depend on, I mean, in this example, you heavily depend on the fact that ZP star is the group of invertible elements of a field. So the field structure here is very important. You use it to do Gaussian eliminations. This method does not apply in any sense to elliptic curves, for example. That's actually great motivation for using elliptic curves.
That's actually maybe the main motivation. Like the fact that like you can use much lower security parameter.
Yeah, you can have
with the same security assurance.
You can have like smaller representation of group elements, and yeah, discrete log is much harder. Yeah, definitely. Yeah, so that's it. Let me conclude with a few remarks. So notable other algorithms, there are many. There is Polig-Hellman, when the group size is not a prime itself, but a multiple of many small primes. Pollard's lambda algorithm, well, if rho was like describing the sequence, then lambda describes some other sequence that joins somehow. This algorithm only applies when x is known to be in a certain interval and the running time depends on the size of this interval. And the most actually cutting edge algorithm is the number field sieve, which is analogous to index calculus. And the running time is this L of 1/3, which is roughly like saying that it's like an exponent of the number of elements to the power of 1/3, something like that.
Number field for factorization.
Well?
Is it number field
Oh yeah, I should say that all these algorithms are good for both discrete log and number factorizations. It's just a matter of how you apply it. All of them are good for both number factorizations and discrete log. Yeah. a bit more on the practical side. How do you choose a prime for a cryptographic system that you design? Or how do you trust the prime for a cryptographic system that you choose to use? So definitely don't. Don't do it yourself, really don't. Other than those like 3 algorithms I described in detail and those other 3 algorithms, there are many other. And there are many mistakes that you can do, including using some specific prime that has a weird backdoor. So don't. Take NIST recommendation, or even better yet, IETF recommendation, or something else that you know and trust and presents you the underlying mathematics. Another note, there is this quantum algorithm, Shor's algorithm. The running times, it's super efficient. It solves discrete log in square root time, not square root, quadratic. Quadratic in the number of bits. That's super fast. But, well, yeah, quantum. And there is currently no sub-exponential algorithm for solving discrete log on elliptic curves. And final remark, the following is the record for breaking discrete log. The largest number to be discrete logged, I guess. So the prime is this prime. I mean, you take the whole part of 2 to the power 766 times pi plus stuff. G is equal to 11, H is equal to something. There is a good reason to choose these numbers. Those are specifically very safe primes. I mean, P is a very safe prime that does not have any backdoor. And it turns out that the discrete log of H to the base of G modulo this P is equal to this number. This was computed in 2016 using number field sieve, using roughly 6,000 core years of what was back then the cutting edge processors, I guess. And
so in practice it was like many cores running in parallel.
Many cores running in parallel, and they were lucky. At the end of the day, it's a randomized algorithm.
And what was the goal? Just
Well, the goal of some cryptographers, this is what they do. They're trying to break discrete log for very large numbers.
Funding for that.
Yeah, so thank you.